Hey everyone, welcome back. We're continuing the series for our final study guide. And I'm sitting with my first period class and they have selected a few problems that they would like to go through. One of the problems that they want to look at is problem number 15. So that's where we're going to start. Okay. On problem number 15 it says write the net ionic equations for the following and identify your spectator ions. So for problem A, this is what it looks like. AgNO3 and it's labeled as aqueous, plus NaCl, and that's also labeled as aqueous, is equal to, let's see, AgCl, this is solid, and NaNO3, aqueous. Okay, so the first step when you're looking at these problems, first of all, sometimes the solubility will not be given to you. So be prepared, have your solubility rules. Of course you're going to have a periodic table, solubility rules, metal reactivity series, all of that stuff will be available to you. But get familiar with solubility rules themselves, all right? All right, so the very first step that you're going to do is you're going to tear apart anything that says aqueous. Anything that is a solid, a liquid, or a gas, you don't split those up, okay? Only the aqueous ones get split apart. So starting on the reactant side, I see this AgNO3 is labeled as aqueous. It's able to dissolve. So we're going to split that guy apart. So you're going to have some silver and you're going to have some nitrate. What you need to do is indicate its charge. So silver, in case you forgot, is on the metal reactivity series. You guys can check his charge. He has a positive 1 ion and he came from an aqueous compound, so we label AQ. The next ion that we have is this polyatomic one. This is actually called nitrate. You would want to look this guy up or something. He's polyatomic. He has an NO3, so we're going to keep the NO3 together. He has a -1 charge, and I'm labeling him as aqueous. So you see how it's charge, aqueous, charge, aqueous. All right, NaCl, that's sodium chloride. You guys are pretty familiar with that guy. He has a +1 charge, aqueous, and some chloride. He's negative and aqueous. Okay, coming to the product side, you have a solid here. Remember, you don't ever split apart solids, liquids, or gases. So since this guy is a solid, you have to keep them together. We are only tearing stuff apart that is labeled as aqueous. So keep this guy together. See how there's no charges on him at all. And then the other compound that is going to get split up is this last one, the sodium nitrate. So we're going to get the charge of the sodium. And that nitrate is polyatomic. Keep him together and get his charge on there. All right, spectator ions are the ions that stayed identical on both sides of the formula, on the equation. So over on here on the left, the sodium is aqueous, and on the right, he's also aqueous. There's your spectator, and the other spectator would be your nitrate right there. And what you have left right there is what we call the net ionic equation. Net ionic equations have no spectator ions left. All right, so that was part A. Let's do part B. K2SO4 and some lead nitrate is going to give you KNO3. And notice how this time they're not labeling solubility on the products, and PbSO4. All right, so you would want to grab your solubility rules, and for the first compound, KNO3, first of all, potassium is an alkali metal. All items with an alkali metal will always be soluble, but there's also another rule for nitrates. All nitrates are soluble too. So this guy is definitely soluble, so we're going to label him as an AQ. The other guy, though, we're going to want to double check. So the rules for sulfates. Can someone grab that and kind of read it for me? So it says all sulfates are soluble except calcium, strontium, barium, mercury, lead, and silver. So sulfates are supposed to be soluble unless they have one of those weird exceptions on there, and lead is on that exception. So this normally would be soluble, but because we have an exception to the rule, we have to label him as solid. He's a precipitate. All right, so the next step is to take all the things that say AQ and break them apart. Okay, so this time you have potassium, and you see how you have a little subscript. This means that it took 2 potassiums to make this compound. This is called potassium sulfate. So for potassium, he's an alkali metal. He has a +1 charge. But how do we indicate two potassiums when we're doing the net ionic equations? What do you do to indicate more than one ion? There's a rule for that. Yeah, you have to put a coefficient in the front. So we're going to place a 2 in the front. Notice the subscript went away, and now we have that as a coefficient. So the rule here is that if you have more than one ion in the net ionic equation, stick a coefficient in the front to indicate more than one. All right, sulfate is polyatomic, and the formula for sulfate is SO with a tiny little 4. So you know how this subscript became a coefficient? The reason why this subscript is staying is because that is the formula for that polyatomic ion. If you rip that 4 off of the oxygen, it's no longer sulfate. It's something else. So we're gonna keep that little 4, put his charge, he's a -2, and an aqueous. All right, we got some lead. And this particular lead is connected to 2 nitrates. So lead can have multiple charges, and I think on the, let me check, on the metal reactivity series, yeah, if you look at lead, it can either be a +2 or a +4. So how can you tell which one you've got? Because you need to indicate his charge carefully. The only way that you can tell is by looking at the anion right here, okay? So this is nitrate, and if you look him up, he has a -1 charge, but you see how you've got 2 of them? That would make the overall negative a -2. If this is -2, guess what your lead has to be? A +2. So sometimes you'll have to kind of figure out what the charges of those ions are, and so that was a good example of when you have to do that. So this is a +2 ion. All right, nitrate, polyatomic, he's NO3. He has a -1 charge, but you see the parentheses wrapped around this polyatomic ion with a little 2 on the outside? You have more than one of these ions. What do you think I'm going to have to do right here? Use a coefficient. That's right. All right, and he's aqueous. All right, one of the steps that I actually forgot to throw in, and I'm seeing it right now, I don't know if you guys see it. What did I forget to do on that? Yeah, balance equation. So I'm going to stick a coefficient right here, because I realized that I needed to do that right now because I'm looking over on the left. Do you guys see how you have 2 potassiums and 2 nitrates? Yeah, here's your potassium nitrate right here, and you got to make sure that your reaction is balanced. So anyway. Okay, so let's split this guy up now. So we have a coefficient indicating that we have 2 of these compounds. So I'm going to keep the 2 coefficients that I had originally on the potassium and on the nitrate. They follow. They should, because it is a balanced reaction. All right, and then you have a solid product here, lead sulfate, so keep him together. No charges or anything, just put a solid there. All right, so there's the whole thing. It's really long. Try to identify who the spectator ions are, things that stayed the same on both sides. I think it was pretty obvious that it was the potassium and the nitrate. Those are your spectators. All right, so number 15 is done. All right, the next question that we are going to be looking at is question. Okay, so we're moving on to our next problem, which they picked is number 19. All right, it says a sample of compound contains 7.89 grams of potassium, 2.42 grams of carbon, and 9.69 grams of oxygen. Determine the empirical formula of the compound, which has a molar mass. Determine the empirical and molecular formula, which has a molar mass of 198.22 grams. 198.22 grams per mole. All right, empirical formulas can be built off of mole ratios. What you have right now is a mass ratio. So the very first step that we have to do is change all of these masses into moles. So that's what we're going to do. So empirical formulas. The key concept here is you have to have mole ratios, okay? All right, so for potassium is 39.1 grams per mole. 39.1 grams per 1 mole. For carbon, it's 12.0 grams per mole. And for oxygen, it's 16.0 grams per 1 mole. All right, let's do it. This comes out to be about 0.202, and that's our potassium. This also comes out to be about 0.202 moles. 9.69 divided by 16. And this last one is approximately 0.606 moles. I think some of you guys might be able to see the trend. Do you guys see it? It's not that hard to identify. Can you kind of tell what the ratio might reduce down to? Do you see a pattern? Yeah, I can totally tell. I can see it. But technically in the steps, like if you're trying to keep track of how to do these problems, the next step would be to reduce. Try to reduce this down to a ratio that makes sense. And the best way to do that is to divide by the lowest value that you calculated. The lowest value that we calculated is 0.202, so that's what I'm going to do. I'm going to divide each of these by that. Okay, and obviously that's a 1, that's a 1, and this will be a 3. So our empirical formula has been established as, if you look, we have 1 potassium, 1 carbon, and then 3 oxygen. So that's what we would identify as our empirical formula. So what we do at this point, because there's additional information, this right here is your empirical formula, so you may want to label that. Okay, empirical. The empirical formula is a formula which represents the lowest whole number ratio between all the atoms. So you see how you have like a 1, and a 3? Okay. But we also want to make sure that what we have matches this mass that they provided. They gave you a molar mass of 198.22. So we just kind of want to see how this guy's empirical formula, how his molar mass compares. So what I'm going to do is the molar mass of this guy's compound. Potassium, again, was 39.1 grams. Carbon is 12 grams. And oxygen is 16 grams. But make sure you realize you've got 3 of those. So let's add up and figure out what that guy's molar mass is. Looks like his molar mass is approximately 99.1. So look at this mass that they gave us, 198.22. 198.22. Do the molar masses match? No. Okay, so what do you think we have here? Is this the molecular formula? No. Sometimes what you have is you have a situation in which you need to double or triple or quadruple the empirical formula to make their molar mass match what was given in the problem. So, all right, here's this guy's molar mass, 99.1. How many times does 99.1 fit into 198.22? So I already divided, I can kind of do that in my head, 2. Okay, check it. It does. It divides by 2. So what that means is that the empirical formula needs to be doubled in order to match that molar mass that was given. So we're going to double everything. Instead of having 1 K, we're going to have 2. Instead of having 1 carbon, we'll have 2. And instead of having 3 oxygens, we'll have 6. And so that's your molecular formula. And there you go. All right, so the next problem we're going to look at is problem number 27. All right, let's check it out. It says, describe what a saturated, unsaturated, and supersaturated solution is and how they behave at the atomic level. All right, this was an area of struggle for some of you guys when we were doing those quizzes. All right, so I'm glad you guys asked about this one. All right, so let's just pretend. I think sometimes drawing pictures will help. Okay. All right, so we have, let's just pretend, a container of to this container of water, we're going to add some kind of solute. Let's pretend that we add maybe like NaCl, okay, just salt. And we dump that in. So originally, the crystal will sit down on the bottom, and the water will come by and it'll attack that salt crystal. And eventually what you're going to make is you're going to make some sodium ions, and you'll make, you know, some chloride ions. But if the solid completely goes away and there's no more solid compound left, What you have just created is something that is called an unsaturated solution. Unsaturated solutions can technically dissolve more of the solute. It's still capable of dissolving more of the solute. But if we add so much salt, so many of these solid compounds, and we've got like a ton of solid salt crystals, and this becomes packed with ions, absolutely packed. You know, the water is just full of chlorides and sodiums. Eventually what will happen is that solid will become incapable of dissolving at anymore. Like what will happen is at the atomic level, for every time a chloride ion pops off of this crystal, you will have another chloride ion that will return to the crystal. So what we say is that the rate of ionization will equal the rate of solidification. When this happens, when this happens, right here, you have reached what we call a saturated solution. A saturated solution cannot dissolve anymore. There's no more room in the solution for these ions. All right, so we just talked about unsaturated and saturated. Now, to create a supersaturated solution, you have to do something special. You have to heat this solution up. So when you heat it up, the water molecules will start moving around at a faster rate. And that will actually cause more bombardments, more at the atomic level. More of the water will bombard that solid crystal, and it'll make it capable of dissolving more because of that higher temperature. So at that higher temperature, you will actually be able to dissolve more of the solid. Okay, so the solid will potentially go away. The solution will become absolutely packed, jam-packed at that higher temperature with ions. Now here's the trick. Once you have dissolved all the crystals at that higher temperature, you are going to slowly bring the temperature down, remove it from the flame, cool the solution down. And in some instances, not all, but in some instances, what will occur is as it's cooling down and going back to that original temperature, the solid crystals won't come back. You've created a hydrated, supersaturated solution. And so when the crystals do not come back at that cooler temperature, that is what we call a supersaturated solution. The ions are literally suspended in solution, just waiting for an opportunity to crystallize. And so as you saw when I showed you some of my supersaturated solutions in class with the demonstration, all it takes is for me to just like blow on the top of the solution, or remember those hot packs, pop that little disc that was inside and give the ions a place to crystallize. Once you give the ions a place to crystallize, the solution will just and crystallize. It's a pretty amazing process. All right, so that was question number 27. The last one that we're going to look at is question number 32. So let's do it. All right, so they give you 35.4 grams of magnesium nitrate, Mg, NO3, 2 to 250 milliliters of water. Okay. It says, what would be the new freezing point of the solution? All right, so refresh your memory. Delta T is equal to K sub F, since we're talking about freezing, times molality times the Van Hoff factor. Okay. So this ionic compound, you would probably have to figure out what that formula was. I kind of cheated and gave you the formula. Mg is a positive 2, nitrate's a negative 1. Okay, so this is an ionic compound. What do you think his Van Hoff factor is? When he dissolves, what will he make? He will make 1 magnesium ion, and he'll also make 2 nitrates, right? What's the grand total there? Yeah, he has a Van Hoff factor of 3. Now, molality is actually moles of solute per kilogram of solvent. Okay, so we're only looking at water here. Okay, so the problem actually gave you guys 2 different values, so you need to make sure that you're looking at the freezing point constant. So the K sub F value is 1.86 degrees Celsius per molal. All right, so unfortunately what they gave you is they gave you the mass of the solute, so we kind of need to convert that into moles. So 35.4 grams divided by, what's the molar mass, guys? Say it again. 148.3 grams per mole. And what's the correct answer, guys? 2387 moles. All right, and then if you look at the mass of the water, that's our solute. We do know that the density of water is, for each milliliter, that's a gram. So this is actually 250 grams of water, but we kind of need that to be in kilograms. So just move the decimal 3 times, and that would be your kilograms. All right, so it looks like we kind of have everything lined up, so we're just going to plug this into the formula and get it gone. All right, let's see, so K sub F is 1.86 degrees Celsius per molal. The molality, I'm just going to plug in the values that we've got here, 0.2387 moles over 0.250 kilograms, and the Van Hoff factor is 3.